Good afternoon, everyone, and good morning to those from the Middle East. Thank you for joining our point source testing webinar today. We will start the webinar now. I am Stan, Marketing Manager from Element Materials Technology, and I will be facilitating the webinar today. First, I welcome you to today's webinar, brought to you by Element Materials Technology. Before we get started, I'd like to cover a few housekeeping items. If you have any questions throughout the webinar, you may submit them on the right side of your screen, and we will address as many as possible during our Q&A session at the end of the webinar. If there are any questions we cannot get to, we will follow up after the webinar. Today's presentation is being recorded. The link to the recording will be available on element.com and emailed to all registrants. After the webinar, a short survey will ask for your feedback. We would greatly appreciate it if you could take the time to share your thoughts. And finally, there have been reports of GoToWebinar freezing or losing audio in the past. So if the webinar seems to freeze on you, our first recommendations for troubleshooting is to try refreshing your browser. Element is a leading global provider of testing, inspection, and certification services for a diverse set of end markets, where failure in service is simply not an option. At Element, our mission is to make tomorrow safer than today for more than 60,000 customers spanning various industries. Our experts have secured over 1,000 accreditations and approvals, actively engaging in the development of global standards. Through our commitment to safety, quality, and performance, we strive to contribute to an advancement of a better world. It is my pleasure to introduce you to our presenter today. Our speaker is Mr. Alex Hardie, a technical specialist for our environmental division in the MEAP region. Alex obtained his master's degree in public health and environmental engineering and has more than 2 decades of experience supporting and consulting customers across the globe in chemistry and environmental. During the Q&A session, Alex will be supported by additional environmental experts from the Middle East and Singapore. Mr. Andrew Poliser and Mr. Sean Zhou are here today to answer all your questions. And without further ado, I will hand it over to Alex to take this forward.
Good morning and good afternoon to you all. I thought I'd just take a quick tour of the agenda as what we're going through. A little introduction to point source emission testing, what it is, why we do it, bit on health and safety, some methodologies, facilities, some monitoring techniques, and then a look further afield at the way that this particular monitoring is moving towards more automated systems, CEMS, or even PEMS in the future. So at the end of all of that, we will then move forward, as Stan was saying, onto a Q&A session where I'll be joined by my colleagues from Singapore and from the Middle East. Just one thing to point out on this is that doing emissions monitoring is inherently hazardous. We're working at height. Sometimes some of these sources are 50, 60, 70 meters high. We're working outside. We're working with hot gases, toxic gases, heavy equipment. So I'm not going to go through all of this, just to point out that there is clearly a major health and safety issue associated with doing this work. And one of the very first things that must be done if you are either performing this type of work, or for that matter, if you are requiring it to be done and hiring a third party such as Element to do it, one of the first things that need to be done is sit down, go through all the risks, go through all the hazards and the risks associated with that, and develop a safe working plan. So that's there's just some general risks there. I'm not going to go through them all, but as I said, or as Stan said, this will be on a recording, and please take your time at a later date to look through these, and always take them into consideration when you are doing this type of work. I think it's probably well worth pointing out that we are looking at point source emission testing, so it would be very, very useful, one would imagine, to at least decide what a point source is. By definition, it's a single identifiable source of air or pollution with a negligible area. It can be modelled as a single point, as a mathematical point in various modelling. It does not include diffuse areas of pollution such as roads or whole refineries, airports. It is quite simply a small single point located source, which may be a chimney, it may be a generator stack, or that type. But they're obviously very common, and it's worth having a look. If we have a look at the next slide, we can go through where these you may find these. As you can see, a fairly obvious picture there on the right hand side, a photo of a standard stack, which is of a minimal area, and clearly can be modelled as a point source. Where would we find these things? Obviously electrical power stations, generators, again, as I said, even combustion engines, large plants, generators, etc., can be considered as single sources as well. They may actually be mobile, but they are single sources and can be modelled as such and considered as a point source emissioning. We also find similar vents or stacks in industrial processes, refining, food manufacture, all sorts of industrial processes where those processes involve emissions to atmosphere. Even within petroleum industries, as I said, I'm based in the Middle East. A lot of refineries have point sources as well, where they are disposing of waste gases, solvents, etc. They may be flares. All of these are classed as point sources. What would not be classed as a point source in something like a refinery would be fugitive emissions from pipelines, etc., covering the whole area of the refinery. They're more diffuse and would not be taken as point sources. Other very common areas, waste disposal, huge interest, a lot of interest these days of waste to energy. But clearly there are hazards or risks associated with burning waste, industrial waste, commercial waste, hospital waste. All of these incinerators have to be working efficiently to obviously ensure that there is no release to atmosphere. In terms of doing the actual monitoring itself, as I alluded to earlier, there are three main ways of doing this. In the older type plants, this is done manually by periodic measurements by companies like ourselves, perhaps. We will come along once every 6 months, once every year. We will physically monitor the emission gases within those stacks using a number of techniques, methodologies, equipment that we'll talk about later. That is done in smaller plants, but more and more, or in older ones, but as well, but more and more on larger scale type refineries, plants, certainly in power stations. there is a requirement now from regulators, both nationally and locally, that these stacks will contain what's known as continuous emissions monitoring systems, or CEMS, where those effectively do what we do, but they have all of the emissions monitoring equipment installed into the stacks, so that they are giving real-time emissions data that is provided to the plant operators. And more and more these days, that real-time data is fed directly to regulators. So the regulators can be checking whether these plants or these particular stacks are meeting their emissions discharge consents. That's very common. What is now becoming more common is what's known as Predictive Emissions Monitoring Systems, PEMS, where there is no physical monitoring of the actual emissions performed, but software is provided using various algorithms that takes all the input data into those stacks in a boiler, say, in terms of pressure, temperature, fuel types, and on the basis of that input data, it can predict the expected emissions coming out of that. So that's becoming much more common now as well, PEMS, but certainly there is a place for all of these three types of emissions monitoring going forward. Why do we do it? Very brief talk about the different types of monitoring, but why are we doing it? The very obvious question on the answer to that is to comply with either local or national environmental legislation. All major plants and even small sort of factories that have things like paint booths or even small boilers will have some emissions consent issued as part of their license to operate. So clearly, if as part of that license to operate by the regulators, there is an emissions limit, you've got to be able to prove that you are meeting those emissions limits. So that's where people like ourselves come along. We will do that monitoring periodically if there are no automated systems in place. That information is then shared with the regulator on behalf of the plant operators to ensure that they are meeting their legislative requirements. Lots of other reasons, as I said, CEMS and PEMS are installed, but once they're installed, you've got to prove that they work. So even in automated systems, there is a requirement for periodic manual monitoring to compare that manual data against the automated generated data to ensure that the CEMS are working and that the PEMS algorithms are correct. A lot of other reasons, a lot of EIA work, but clearly one of the very good advantages of being able to do this is that if you're a plant operator, you want to be able to know that all of your systems are operating at the maximum efficiency. So in terms of collecting data, you can tweak your plant processes to optimize efficiency and minimize emissions or harmful emissions. A lot of other stuff in there. We get a lot of performance criteria meeting, where if you're buying a large generator, you will buy it with performance criteria limits. In other words, the supplier will tell you that operating at certain parameters, what those emissions from that particular generator would be. So as part of the commissioning on that, as part of the signing off on it, companies like ourselves would come along and monitor those emissions to check that what the manufacturers are selling is meeting those requirements, and of course those requirements will tie in with the plant operating licenses. Finally, although it's not carried out much here in America, it is used for emissions trading. In terms of, we'll look at the different types of monitoring in detail, but we'll have a quick look at the manual monitoring, which is the sort of stuff that parties like ours will do. I'm talking here about US EPA monitoring, whereas we will discuss a little bit about European standards as well later. But in terms of US EPA, there are two different types of monitoring methods. Reference methods or promulgated methods, a couple of them are there for oxides of nitrogen, method 7E chemiluminescence, or method 5 for isokinetic sampling. These are reference methods. They state the type of equipment that must be used, the techniques that must be used, and the performance criteria of those methods. These methods are required for regulatory purposes. However, the US EPA allows other methodologies called conditional test methods, which are less stringent, have a lower tolerance level in terms of accuracy, and can be done much quicker using handheld equipment. There is clearly a place for this. Generally, these are done by plant operators themselves, where they are just checking routinely on a daily or a weekly basis their emissions if they don't have CEMS in place. They're checking for plant optimization information, or just generally checking that they are meeting criteria. So there's a place for both of these methods. Element carry out both, but in general, as I said, the reference methods are used for regulatory purposes. The conditional test methods are used as a rapid indication of plant operation, and if you're meeting those legal requirements. Move on from there. As I said, looking at the reference methods themselves, generally split into two as well. Sorry about breaking all this down into different bits, but you will have time to look at this online. They're broken into two main categories: direct reading, instrumental techniques, which are generally used for gases, where we are taking direct readings within the stack, and secondly, manual isokinetic methods, where we are abstracting gas from the stack, trapping that material onto filters or in some sort of trapping medium, caustic or acid, and then using that, taking those samples into a laboratory for subsequent analysis. Isokinetic sampling is done for particulates and anything that may form particulates, such as PEHs, dioxins, metals, etc. They're not being read directly in the stack, they've been read or tested for outside. In terms of direct instruments, just while we're on this, you can see a couple of very large stacks there, and you can see the platform at the top. That's where companies like ours or our staff would be operating at great height, and the analysis is performed in an air-conditioned lab at the bottom. There's a lot of equipment to be carried up there at great heights, so as I said, just to point out that all of these sort of things have to be taken into account. Just some information, just again, a slightly extended list of direct reading methodologies for oxygen, carbon dioxide, etc. We would be taking samples directly from the stack, transporting them to ground level, and analysing them within the air-conditioned lab at the bottom. So a lot of things that need to be considered. We need power, we need safe operating procedures. So just gives you a picture of what we would do. Just on just a photograph there of some of the types of equipment that we would be using for monitoring of these gases that are located within that within our lab, mobile lab at the bottom. So as I was saying, there's also conditional test methods. You can see there the type of equipment that's used. It's a lot simpler. It will do multiple gases at one time, again, and can be carried up direct reading in the stack, US EPA CEMS 30. very useful, simple to operate. It gives rapid, fairly accurate results. Very useful for just checking your own compliance, maybe getting information for process control or optimizing parameters. Very, very useful technique, and there is always a place for it. Isokinetic sampling, as I said, this is used for any particular types of possible pollutants, such as dust, clearly PM10 or PM2.5, but anything as well that that will be trapped as a particulate, like metal particulates, even acid gases that will be in particulate water, any of these sort of things. So it's very important, because the analysis is not done directly from the stack gas, but that we are taking a sample of that gas, trapping the contaminants on that in a medium, such as a filter or through acid or even in water. Then it's extremely important that we are able to extract that sample in such a way that we are absolutely aware or know that we can tie the rate of that abstraction to the rate of flow within the stack, so that we can calculate the results in a meaningful manner, either as milligrams per cubic meter within the stack, or perhaps even as total emissions. So isokinetic sampling, what does it really mean? Well, it's pretty obvious. Iso is from the Greek word meaning equal, and kinetic is movement. So what, as I said, what we are aiming to do here is to be able to abstract the gas from the stack in such a way that we can relate the abstraction volumes or the abstraction flow to exactly the flow within the stack, that will then allow us to calculate the results accordingly. So that's just a little diagram. From there, as I said, why do we do this? It's extremely important that that we can relate the analysis results in the lab to the absolute concentrations or an emissions concentration in the stack. We need to do this because we can't sample the particulates easily, because there will be turbulence within a stack. There's gravity effects. There are different thermal behaviors move particulates around. So it's extremely important when sampling for particulates that this is done very, very carefully indeed. And it's quite important when you're doing this for isokinetic sampling, because, as I said, there may be areas of turbulence within a stack that may be caused by other probes within that stack. It may be caused by bends within the stack. There may just be thermal turbulence. So it's not a simple matter of going along, putting a probe in and abstracting a sample. You have got to ensure, as I said, that that sample is representative or can be calculated back to the stack. So generally this means, for isokinetic sampling, doing multiple sampling points within a plane, sometimes at 4, sometimes at 2 different locations, but this is just a general idea for a drawing of a circular duct and the possible number of sampling locations that may be required depending on stack conditions. But as you can see, there often is it's not a number of samples or a number of sampling locations that need to be taken. Just again, for rectangular ducts and other shapes of ducts, then there are certain sampling points, geometric points that where we have to be taking to ensure that our isokinetic samples are representative. All of this type of information needs to be known prior to us arriving on site, so that we have the appropriate sample probes, that we know the numbers of locations that we need to be taking. So it's all about planning and making sure that the appropriate reference methodologies are followed. Again, we talked before. I talked a little there before about the facilities that we will need to do this sampling. We have quite a lot of equipment that needs to go up to these sampling ports. Some of these probes on large stacks, we are looking at up to 4 sampling probes or sampling points in the stack at 90 degrees. We can usually get away with 2 at 90 degrees in some smaller stacks, but all of those types of sampling ports have got to be there. We've got to know that before we start. But you can see that some of these probes can be 1.5, 2 meters long, even longer, so that we need to make sure we have effective space on these platforms to operate safely. Just again, an idea of a picture of what's going on. You can see that's actually in happening on a circular stack. We are looking at up to 4 sampling ports that clearly have to be in place at 90 degrees. And you can see us operating at quite a height. And some of these probes, as I said, are several meters long. So part of the planning process is to make sure that these sampling facilities exist, that they are adequate to allow us to do the testing in accordance with the reference methods, and they are sufficient that we can safely operate at these heights in definitely in the Middle East and outside temperatures that may be 40, 50 degrees, and with gas temperatures running into several hundred degrees. I'm not going to go through this, it's just to give you an idea of the type of isokinetic sampling equipment that is required. You can see the nozzle. The probes are of various lengths depending on the diameters of the stack. We need heater boxes and glassware for entrapment, controllers. A lot of this kit has to go to the top of the stack. It can be 40, 50, 60, 70 meters. So again, it's not just a case of putting that on someone's back and climbing a ladder. Is there winches there? Have they been tested? Is there sufficient room for us to be putting this this equipment on the sampling platforms? Just to give you an idea of what this stuff looks like. Just to to go through that again. Where are we looking to put these sampling locations? That's very important. We want to avoid disturbances within the flow as much as possible, away from bends or fans or any other probes that may be present. We're looking for ideally a vertical sampling plane, but we can do it horizontal. We're looking for reasonable flow rates, so there's not too much swirling or flow within their sampling ports. If you're doing isokinetic sampling, we're looking about preferably 4 on large ducts, but or stacks, 100 millimeter to 125 millimeter diameter as a minimum, to allow us to get the probes and the sampling ports in there. And again, I've said there before that the platform has got to be adequate in terms of load-bearing capacity, winches, getting a number of people up there safely and operating safely. So all of these things are things to consider when we're doing this. Again, just having a quick look at this, and as I was saying at the very beginning, this type of work is inherently dangerous. So it's very, very important that each and every one of these particular potential risks are looked at and considered prior to starting any site works, to make sure that everyone is safe. That covers quite simply a lot of the manual periodic monitoring that ourselves and various other companies like us would do on behalf of clients. Generally, for clients who don't have their own emission systems in place, we would do this on a 6-monthly or a yearly basis, provide them with the data that they can provide to their local or national regulator to ensure that they are meeting their discharge consents. In the last maybe 10, 20 years or so, more and more requirement is coming in, certainly for larger plants, and for new builds, that these stacks are equipped with what's known as continuous emissions monitoring systems. As I said earlier, basically these systems are what we do, but built into the stack themselves. This allows the operator, and in many cases the regulator, to have real-time access to what is happening in that stack. As you can see in the simple little drawing there, it's very similar to what we do. So, you know, there are probes. The probes will take the samples, take the reading, direct readings for gases. We'll take abstractive samples for particulates. Well, they will usually do that by light scattering and things as well. So there's a lot of different types of monitoring. This can then be used, as I said, for not only for real-time data for regulators, but also allow the plant operators to optimize the processes. Very common, CEMS will do NOx and SOx, etc. However, that's all well and good, but how do you prove that these CEMS work? For two reasons. If you're a plant operator, then you may purchase a CEMS or as part of the commissioning. But clearly, you want to know that once that CEMS has been installed, that it is meeting the requirements that you set while purchasing it. And also, the regulator will require that the operators can prove those CEMS are working before they will give them a license to operate. So there's quite a lot of standard CEMS quality assurance procedures. We do a lot of work out here in the Middle East based on US EPA standards, but certainly we also do work on European standards as well, and I'll talk about them in a minute. But in terms of the US EPA, for CEMS, there's two main regulations: US EPA CFR 40 and CFR 75. So what are the differences in these? If we will have a quick look at that. Yeah, Part 60 is generally a less stringent requirement, and it will cover many of the different parameters, looking at emissions limits in milligrams per cubic meter of gas. It also looks at how do we check that those CEMS are operating correctly, and gives various performance criteria for them. 75 is a bit more stringent, and it contains a couple of other requirements such as linearity and cycle time. It doesn't appear in 65. It's an absolute requirement if you're looking at emissions trading. Again, we're operating both to Part 60 and Part 75. That is up to the plant owners and the regulators to define what particular criteria they require to operate at. But both of these requirements include what's known as RATA, which is a relative accuracy test audit, which can be used or is used to prove the accuracy or otherwise of those CEMS. But I'll come to that in a minute. As I said, relative accuracy test audit. What is it? It's a way of proving that if you have installed a CEMS, that CEMS is working. At its simplest, it's a matter of testing the data, the test data on the CEMS, with data generated by companies like ours, doing simultaneous monitoring using reference techniques, US promulgated methodologies, and making a comparison of those sets of data. Clearly, there are then acceptance criteria for those data, which vary slightly between Part 60 and Part 75. But this is an absolute requirement if you are installing CEMS. Clearly, you want to know if it works, and the regulator wants to know if it works as well. So that is done by what's known as RATA. As I said, many reasons to do this. The principal one is that it's required by the people who are buying it and the regulators to prove if you've got a CEMS. And I've said PEMS, we'll come very to that in a few minutes, that those continuous systems, whether they are actual manual monitoring systems or predictive systems, you have to be able to prove that they work. And as I said, that's where companies like Element come in to provide that testing to prove that. Again, you can use it to make sure your CEMS are working on an ongoing basis. Normally, it's annual testing of CEMS, so it's important not only that you prove that once you've installed it, it works, but you have to be able to regularly prove that it continues to work. Again, I'm not going to go through this in too much detail. Under normal CEMS, it's important that we are operating at a minimum of 50%, greater than 50% load when we are doing this testing. And conditional test methods are not permitted to do under USCP regulations to do RATA, which makes a lot of sense. As I said, the conditional test methods have a lower level of accuracy, and clearly if you are doing this testing to prove that your installed CEMS is operating satisfactorily, you need to be doing that to quite a high standard. So again, I'm not going through all of that, but you know, the information is there as to what needs to be done. In terms of how we would do RATA in particular, you carry out a minimum of 9 sets of reference tests at 3 represented locations, greater than 50% load. So it's multiple sampling across multiple locations on the plane within the stack. We need to be collecting adequate data to ensure that statistically that data is valid, and then we compare that data against the data that is output by the CEMS. And again, that's just a little bit of information as to then what we do with that data. There are various allowable tolerances depending on the types of gases, the concentrations expected, and we would then make those comparisons and write reports to see whether that particular CEMS has passed the RATA test and is therefore fit for purpose. Just a little summary there of the difference between Part 75 and Part 60. On the left, we have the initial requirements for CEMS verification during installation and commissioning. And you can see that Part 75 is a slightly more stringent criteria. It also includes additional tests such as linearity and cycle time. But more importantly, going forward, there is ongoing tests. It's not acceptable, it's not good enough to say, we've installed our CEMS, it works, thank you very much, and never look at it again. So you can see on the right, there is ongoing quality control requirements for CEMS in terms of daily, or quarterly, and annual monitoring at various tests that are carried out. And some of these should be carried out by the plant operators, and some should be carried out by third parties to ensure that the CEMS continues to work satisfactorily. So again, if we quickly move on. Just a little word about the European standards, which again we are being asked to do a bit more here in the Middle East. EN 14181, which has Qual 1, Qual 2, and Qual 3, and what's known as Qual 3 is the annual surveillance test. Qual 2 is the equivalent of a RATA test. That's slightly different. But they differ a little bit in terms of their amount of the amount of testing required, but generally they are very similar. If we can, the difference in Qual 2 is that in RATA for US EPA, if you're following the EPA regulations, Part 60 or 75, RATA has to be done annually. Whereas the Qual 2, which is the commissioning test under EN 14181, has to be done every 5 years. However, they have what's known as the annual surveillance test, which is effectively a reduced Qual 2 to be done on an annual basis. Just a little bit there, if we just move on, Qual 1, we're looking at various tests there, Qual 2, ongoing monitoring, Qual 3 as an annual surveillance test. So the similar, the methodologies, the testing is pretty similar all round. A bit more detail as what's required in there. So you can see that for Qual 2, we're looking at doing sort of 15 series of tests. On an annual surveillance test, we're looking at 5. So it's a reduced Qual 2, but there are certainly equivalencies between the European methods and the European standards and the EPA standards, but it is important to be aware of what is required within your particular geography. As I said, Qual 2, 15 sets of reference over 3 days, but it's only done at commissioning and then done one every 5 years. And then we have what's known as the annual surveillance test, which is 5 sets of tests. Very similar to RATA. Again, there is obviously in the standards performance criteria that need to be met, which is again just simply comparing the data obtained by companies like ours using essentially a mobile CEMS against the installed CEMS. So you can have a look at that later, but it's important, as I said, to know what the regulations are installed in your particular geography. And more going forward, is we found that people are working towards PEMS. So it's now becoming quite common. It was used less frequently, or a lot of regulators were uncomfortable using PEMS because the software in a lot of the models had not been developed adequately in their opinion. However, that's moving. What PEMS are, as I said, they are completely software solutions that take input data and on the basis of that input data will output a predicted emission. So effectively we have different methods of doing this now. More and more governments are accepting PEMS, so you know, they are becoming much more common. As I said, they are predictive. They do not take any real-time readings. They will take the input data to the stack, the composition of the gases, the turbine temperatures, pressures, humidity, etc., the type of fuel, and then they will, on the basis of that, make a prediction as to the various emissions that are being produced. These are becoming much better now in terms of a lot more information, a lot more data from the companies who have put these in place. So that's they're becoming much more accurate now, and as I said, because of that, they are now becoming a lot accepted much more readily by regulators globally. PEMS is treated very much like CEMS. You can't come along and say we've bought a PEMS system. Thank you very much, regulator. This is the output data. In that respect, PEMS is very much like installing a CEMS. It needs to be you need to prove that it meets its requirements. We do a lot of work on PEMS. As I said, the companies that produce these models have got a lot of background data, so they usually start with a reasonable set of software algorithms, but in each case it needs a bit of fine-tuning. So we will go out, we would collect real-time data that will then be compared to the predictive data, which will allow the PEMS providers to do a bit of fine-tuning on the software to ensure that that eventually they come to a system where the predictions are meeting the true values that we're getting. But again, that all has to be done initially. Again, we need to do RATA on PEMS once it's installed and before it's allowed to be used. Very similar to how we would do with the CEMS. And thereafter, there are requirements for looking and ongoing monitoring of these PEMS. So, just looking at this, as I said, the PEMS need to be calibrated. You have to be able to prove that that the predictions from these software algorithms is actually matching the true emissions. So again, we're looking at this in terms of doing a calibration, doing a RATA testing on a PEMS. We're looking at doing this at the 9 referenced methods, but generally we're looking at doing it at different loads. You've got to be able to prove that your algorithm operates at is working effectively at the different loads that perhaps the system may be operating at. And again, we're looking at what's known as a relative accuracy audit on a quarterly basis, which can be reduced to 6 monthly. But even PEMS require annual RATA to be done by external parties like ourselves, using reference methodologies. But as I said, they are becoming much more accurate now and much more widely implemented and accepted. As I said, that's the future. The future is moving from a lot of manual monitoring, which there still will be carried out in smaller plants, towards CEMS, and now CEMS is also being replaced by PEMS. But before we finish, it's probably worth a quick word as to what the disadvantages and advantages of them. The advantages of CEMS. CEMS actually provide real-time direct measurement data. You are having probes within the stack taking measurements using reference methodologies. You, in many ways, can't get better than that, assuming that that your CEMS are working accurately. So the results tend to be more accurate. As I said, they're more widely accepted because of that by governments and regulators, although certainly in the last year or two we have seen a significant move towards PEMS, principally because of the improvement in accuracy of PEMS. So again, there are certain advantages of PEMS over CEMS, there's no doubt about that. PEMS can be much cheaper. There's no hardware. You're not having to put stacks and platforms and probes and all sorts of monitoring equipment there. You are simply monitoring the input data to the stack. So this, typically it can be 20, 30, 40% the cost of a CEMS for PEMS. As I said, there's no there's no hardware involved, so that's much better. And also, a single PEMS can take data from multiple stacks. Clearly, there's a major saving to be had in that situation. Clearly, again, it's that those PEMS, that PEMS has to be proven to be accurate in each of those stacks. But if that can be done, then there's obviously great savings to be made there. Also, because PEMS doesn't actually have any monitoring, physical monitoring equipment, it can be used on sort of smaller stacks, distant stacks, etc., where installing physical monitoring equipment may be difficult on rigs, etc. So there are major advantages to PEMS, and as I said, they are now becoming much more accurate, such that they are being accepted. Then I've came to the end of my talk, and hopefully you found that interesting. And I'll hand you back to Stan, who hopefully can pass some questions on to my fellow panelists, Andy and Sean. And I'll leave you with that. Thanks for your time. I hope hopefully hear from you soon. Thank you.
Thank you, Alex, for sharing the insights on point source testing for efficient emissions management. I now invite Andy and Sean back, and we will now go over and answer some of the questions you have submitted. Note that all questions are anonymous, so if you want to ask our experts anything, please do post in the chat. So there's a first question we received. For transportable PEMS method, does the procedure include steps to provide the stratification of sample taken? Andy?
Yeah, thanks, Dan. Hi, everyone. I think you said stratification there, yeah? Yes, stratification is a routine part of stack emissions testing, particularly when you're looking for things like combustion gases like NOx. So before you do the rata, you need to determine the most representative sampling point within the duct. So you do that by traversing the duct and determining whether the gas stream is stable, laminate, and well mixed. And if you do determine that, you can do single point sampling for your rata. But if you find if it's not well mixed and the concentrations vary across the stack, then you need to go with a multi-point grid sampling approach. Hope that answers the question.
Yeah, thanks, Andy. Let's move on to the second question. How do you compare measurements made by different analytical techniques?
Okay, well, firstly, yeah, there's lots of different techniques for different parameters. So I would say the first thing you need to do is to ensure the units you're measuring are consistent, because some techniques measure in ppm, some measure a mass, some measure a percentage, some may even measure a direct concentration. So first of all, just check the units are consistent. Secondly, I would say it's important to understand how the gases are measured. Are they at the same conditions when they're measured by the analyzer? So some analyzers measure on a dry basis and some may measure on a wet basis. So it's important to understand if you've got a different moisture content value, that you correct for that moisture content within the gas, because it has a big influence on the end concentration.
Yeah, thanks, Andy.
Hope that helps.
Let's move on to the next question. Is stack gas flow rate and mass emission typically determined during stack testing campaign for supporting with pollution inventories and emission factors?
Yes, the flow rate and velocity is routine as well, particularly when we're doing isokinetic, because that's a very important part of determining where the representative points are within the stack. So yeah, we measure the velocity and then calculate that up to a flow rate in meter cubes per hour, for example. Yeah, and that will help with determining mass emissions in tons or kilograms per hour. Then you can multiply that up for your sort of annual emission inventories.
Thank you, Andy. We have a last question. Can elements simultaneously test pre and post filter to support with a abandonment efficiency project?
Yeah, yes, we can do inlet and outlet testing on filter plants. We can mobilize multiple teams and multiple sets of equipment. So we'd have one sampling team on the inlet and one on the outlet. What I would say is for that sort of type of test, it's important to have an understanding of the concentration beforehand that's going in to the inlet of the plant, because obviously concentrations are usually a lot higher because it's pre-filtration, and you need to ensure you can obtain a representative sample and also protect our equipment from overloading and being damaged. But yeah, that's definitely doable.
Yeah, thank you, Andy. That seems to be our last question. So I'd like to thank Alex, Andy, and Sean today for taking us through the webinar today. We hope you find the section informative. So if you have any further questions or need to reach out to our team of experts, please use any of the contacts displayed here. As mentioned, a recording link will be emailed out so you can replay any section or pass to colleagues who may be interested in point source testing. We will now close the session. Thank you very much for joining us today, and we hope to see you on a future webinar soon. Thank you and goodbye.
Thank you.
Thanks, Dan.